Hello, geometry class. Welcome back. Hope you guys are doing well. Today we are talking about the Pythagorean theorem. However, in the beginning, we are going to review some of last time. So if you feel confident on this perpendicular bisector, you can skip this first part. If not, this is a great time to review. So let's practice. We're going to find the value of x. Now let me go a pen out. Remember, if you see here, this is a perpendicular bisector. That word perpendicular means when two things intersect, they intersect at a 90-degree angle. And also that means that we have some similar sides, which is good for us. This saying here that AM is going to be the same as, I'll just say MB, which pathly speaking now, to find the value of x, since we have a perpendicular bisector happening here, I just set them equal to each other. So 3x minus 8 now equals 2x, and it seems pretty simple now to solve for x. So to solve for x, again, we want to get x on one side and everything else on the other. So let's move the 2x from the right side to the left. And we know that 3x minus 2x is a simple just positive x. And then now to get the x by itself, we just need to move that negative 8 to the other side, which is great news because now we get that x equals 8. So the biggest thing here, it was a perpendicular bisector. And since it was a bisector, it's splitting it into two equal parts. So from here, we just set each side equal to each other. We'll see something very similar here. When finding the value of x, again, since it is a perpendicular bisector, that means these two sides would be the same, and these two sides would have equal length. So that means here, it doesn't really give me a point. We'll just say this is, I don't know, C. We'll say that. So let's say here that AC is equal to CB, which is good news because we can just now say, and I'll pick a different color here. Let's do purple. So now here we have 4x plus 4 is going to be equal to 12x. And again, we just need to solve for x. Doesn't really matter what we do here in terms of moving x to either side. Just so we stay positive, I'm going to go ahead and move this 4x to this side. And I do that because now I get 4 equals 8x. And then here to solve for x, I'm just going to divide both sides by 8. 4 divided by 8 is the same thing as 1 divided by 2. Again, with this perpendicular bisector, they're splitting it up to two equal parts. That's the definition of bisector. So that's nice. Nothing too crazy there. Ooh, notice this one. Try this one by yourself for a second. You can pause the video if you like. But we find the value of x. Notice I didn't give you any sides. However, it is a perpendicular bisector. So don't forget, that is a 90-degree angle, which means here, let's pick this color, which means here that angle 3x minus 3, that is the same thing as 90 degrees. Now, yes, you don't really need that degree sign. You can just say 3x minus 3 equals 90. But basically here is you find a value of x, plug it into 3x minus 3, and you better get 90 at the end because this is a perpendicular bisector. So then here, just to solve for x, again, nothing too crazy happening here. Add 3 to both sides. And as I look at this, I realize I need to do some mental math. Because to solve for x, I need to divide by 3 on both sides. Nothing too crazy here. Actually be just 31. Notice x is 31, but not 31 degrees, okay? Because here, if I was to plug in 31, let me get my laser pointer out. If I was to plug in 31 here, Multiply that by 3 and subtract 3. That would equal 90 degrees, which is true because it is a perpendicular bisector. All right. So today we are talking about the Pythagorean theorem. Now you may have heard about this or you may have talked about this in middle school. So it's a great little refresher about what it is, what does it mean, and how is this applicable. Now we'll talk more about the application in class, especially with reference to our triangles. But for right now, I am talking way too much. I brought in a special guest. It's a really big history guy. He's actually pretty great at math and history and actually an artist as well. So let's take it away. Let me throw it to you.
Howdy there, folks. My name is David Crockett. Well, if you don't know who I am, you probably should have been paying attention. 7th grade Texas history. If you know me from famous things, like currently right now, I'm in a situation with this mission called the Alamo, and there is Santa Ana knocking down on the front door. Well, during this little mission, I had to take some time to help out my good old buddy, Mr. Garcia. Now, you see, heard you guys talking about this Pythagoras fella. Well, if you guys didn't know, I'm actually a really big math guy. In fact, you know what? Let me paint you a picture of who this Pythagoras fella is. I'm actually a well-known artist as well, growing up in the plains of Texas. Now, let me get my good old little inkwell. Where's that little sucker at? Oh, that's not it. Let me see. Where's it here? Oh, that might work. That looks weird. And oh, I'm a little inkwell here. So as I draw me a little bit of this Pythagoras fella, for those who don't know, he was born in good old Greece. Not too many people know about him, but he was born in Greece. He had a little cold, as all the young mathematicians did. Let me get a little smudge on this. But and he was so happy when he found this theorem. So happy, elated. Oh, that's a good word. That whenever he found it and discovered it, some say he sacrificed 100 oxen. Now, wow, interesting, isn't it? Well, let's see how this handsome fellow looks like. Oh, that's a beautiful picture right there. It's a beautiful picture of this Pythagoras fellow. Let's look at that. Why don't you look at that? Wow, isn't that just stunning? That's just amazing. Well, this Pythagoras fellow, he discovered this little theorem. So he said here, look at this little drawing I made. Look at that little drawing. Got those colors from different flowers in the plains of Texas. Now, he said, if you take the area of a square plus the area of another square, it's going to equal the area of a bigger square. And now what that means, look like, again, cool. Take that whole area of A, that whole area of B, it's going to equal area of C. And that can be used in this good old little triangle. Now, we will be using that in a bit to actually find the missing side lengths of a triangle. And there's so many different proofs out there. But fellas, today, that's not my goal because I got a battle going on right outside and I got to save this place. I love this place to death. Now, folks, I got a war to fight and that means I got to go. I got to go. I'm going to throw it back to Mr. Garcia. Hopefully, I will see you later. I don't know the outcome of this, but hopefully it'll be good. It'll be fine. It will be fine. Now, let me throw it back to you, Mr. Garcia.
Wow, folks, that was special, wasn't it, man? Thank you, Davey. Again, he has to head out. Someone's at the front door, apparently. I'm not sure who that is. But thank you again, Davey. Hopefully, we see from him again. I don't really know how that battle turns out, so hopefully, we'll see from him again, won't we? But he was talking about this thing called the Pythagorean theorem. So let me get my little laser pointer here. Oh, that's not good. Cool. Perfect. So when a triangle has a right angle, and the squares are made on each side of the three sides, then the biggest square has the exact same area as the other two squares put together. And that can be summarized with the equation a squared plus b squared equals c squared. So the little picture that Davey drew, I have here down as well. But I included this little picture here as well. Because if I was to count the number of triangles within the square, there's 1, 2, 3, 4. So there's 8 in this one, and there's 8 in this one, and there is 16 in this one. It's a kind of a picture example of how the Pythagorean theorem works. So the area of this square, which is 8, plus the area of this square, which is also 8, equals the area of this square, which is 16. And this is so useful and handy for multiple reasons, which we'll see today and in the next class. Couple things about this theorem. Let's see here. Perfect. In this equation, a squared plus b squared equals c squared. C is the hypotenuse of your triangle. Now, what is a hypotenuse? Two things. One, it's the longest side, and two, it's opposite the right angle. Again, it is the longest side and it's opposite the right angle. So if we know two of these sides here, either one of the legs or the hypotenuse, we can find the either side. Now, the thing is, this only works with right angled triangles. So if your triangle does not have a right angle, you cannot use this theorem. Okay? Again, if your triangle does not have a right angle, you cannot use this theorem. Different reasons why, but for us in geometry, since we did not have a right angle, that means we don't have a hypotenuse because the hypotenuse is the side that is opposite the right angle. Now, that is a discussion for pre-calculus where you learn different ways to figure out the different stuff. But for right now, just knowing Pythagorean theorem, let's find the missing side length. So in this case, I have here a leg of 3, leg of 4, and a missing side length of something. So again, it's a squared plus b squared equals c squared. So in this case, I'm trying to find out what is c. But I don't know what it is, so I can use this theorem. It doesn't really matter which side you say is A and which side you say is B. As long as you make, my bad, the legs A and B, you're fine. So in this case, I'm just going to plug in what I know. So I'm going to say this side with the 3 is A. So that's 3 squared. I'm going to say the side with the B, sorry, the side with the 4 is B. So 4 squared. And from there, I'm just going to find C. And now we just actually just simplify. So that first part right there, 3 squared, that is 9. 4 squared is 16. And 9 plus 16 is 25. So we got the length of C squared, but we need the length of just C. So right now I have 25 equals C squared. And I'll write it over here to the side as well, and I'll write it in different color. So I'm close. I'm almost at the value of C, but I got C squared. This is a throwback to Algebra 1 on how to, quote unquote, get rid of that square. To get rid of that square, I'm going to need to take the square root of both sides. And yes, I know that technically that's like a plus or minus, but we can't have a negative for length. So this says here that that missing side is a length of 5. Now, I purposely picked these numbers because this is called a Pythagorean triple. If you were to use this and up these numbers by a scale factor of whatever, you would always have a Pythagorean triple, because then you'll have a case where it always works. Now, these first couple examples are very similar, as in just find the value of C. And again, a squared plus b squared equals c squared. It doesn't matter which number is my a and which number is my b, as long as I stay consistent and don't label any of them c. All right. So I know last time I said the number right here was a. Just to switch it up and show you that doesn't matter, I'll say that one is b. Okay. So here for a, let's say 9 squared. B will be 12 squared. And that is c squared. Now, 9 squared is 81. 12 squared is 144. And this is what it's nice to have a calculator present, because sometimes these numbers may appear big. And if I am correct, that should be 15. Again, I'm checking. Perfect, I was right. So here again, 225 equals c squared. Once I get to this part, I'm not done. I need to find the value of c. Right now, I only have c squared. So here, to find the value of c, again, I want to take the square root of both sides. The square root of c squared is just c, and then the square root of 225 would be just 15. And I think we have another one like that. Yeah, okay, we don't. So again, a squared plus b squared equals c squared. Now, what happens if I'm missing a leg, but I have a hypotenuse? So again, the hypotenuse is the side that is opposite the right angle. So a squared plus b squared equals c squared. Again, it doesn't really matter what you label as a or b, um, but I cannot say 7 is a or b. 7 is my hypotenuse, which would be my c. So here, if I was to plug this in, and I'll just solve for a in this case, okay? So I'll say a squared. I would end up plugging in 5 for b, and I would need to plug in 7 for c. Again, there's wiggle room. It's like, oh, I want to solve for b. That's fine. You're just finding the leg. But here, again, it's still very similar. A squared plus, okay, 5 squared. We just did that as 25. Perfect. Ooh, 7 squared. That would be 49. Ooh, okay. It looks a little bit different, but nothing too crazy here. All right. Our goal is to get a by itself. Our goal is to say a equals a number. So anything that is disturbing that a equals, move it to the other side. So I got an a squared plus a 25. That means let's move that 25 to the other side real quick, okay? Oh, perfect. So to move that 25, I'll subtract 25 from both sides and go back to perfect. So here, a squared, 49 minus 25, 24, right? Why am I blanking on that? That's weird. Cool. Yeah, 24. And now here I'm going to take the square root of both sides. Square root of 24. Is that a perfect square? Think about it. It's not. Okay. That is solely like that. Now, there's a couple things here with this question. Okay. First off, it says find the exact length of the third side. While yes, this is correct, that it is the square root of 24, we're going to go ahead and see if we can reduce this radical. Remember that, reducing radicals? Something you did in Algebra 1. So if I got the square root of 24, remember to break it up. You just break it up with its prime factors, okay? So you're going to write its prime factorization tree. So two numbers that multiply to be 24. Let's do 8 and 3. Does it really matter what numbers we use? Okay, 3. Does that break up anymore? It does not, okay? 8 does. It's 4 and 2. And then here, 4 will break up as 2 and 2. Now, we're finding the square root. Since we're finding the square root, that means I'm looking for pairs. Now, I have a pairs of 2's here. Let me mark those out. And, oh, I have a 2 and 3 left over. Let me go ahead and box those up. So when rewriting the square root of 24, I first did my prime factorization tree. Next, I saw, hey, let me look for pairs of numbers. And as I broke up 8, I broke it up as 4 and 2. And as I broke up 4, I broke it up as 2 and 2. I got pairs of 2's. And then I have a 2 and 3 left over. And so I'll do this in different colors just to make sure we're on the same page. Let me do with green here. So these 2's, that number, that's a pair, will go on the outside. And it's going to be the square root of all the numbers that are boxed up. So in this case, we got a 2 that's boxed up, and then we got a 3 that's boxed up. So that means here on the inside of my parentheses, let me go back to my pen. Inside of my square root, let me bring down that 2, and I'm going to multiply it by that 3. So this ends up becoming 2 square root of 6. So here's the thing with this. If you plug into your calculator, the square root of 24, that would be 4.898, okay? And you also plug in 2 square root of 6, you still get 4.898. So the square root of 24 and 2 root 6 are the same thing. We just found it in exact length. Now, in this case, we can write either one. We would tend to prefer the other one, the reduction. So I'll just go ahead and write 2 square root of 6. If we can reduce the square root, we should. Okay? Let's see here. Find exactly to the third side. Again, same thing. So a squared plus b squared equals c squared. And just to stay constant, I'll say I want to find out what is a. Okay? So here, a squared, well, we just saw that 15 squared was 225. And again, 39 squared, use a calculator. Don't torture yourself. 1521. So here I'm going to do 1521 minus 225. So yeah, be 1296. So it's 1296. Is that a perfect square? If you don't know, plug it into your calculator. It doesn't hurt. So as we take the square root of both sides, if we get a whole number, that means it's a perfect square. If we get a decimal, that means we need to see if we can reduce this square root. And again, the reducing square root we just did in the last one. This case, we're lucky. We actually do get a whole number. This value of a is 36. They got a couple more here. Yeah, I got about 3 more. So find the third side in simplest radical form. Again, same thing here, 8 squared plus b squared equals c squared. Again, it doesn't matter if I'm solving for a or b, just pick one. I'll tend to say that I'm solving for a. B again is 6, and c would be 11 in this case. Now here, 6 squared is just 36, 11 squared is 121. And when I subtract 36 from both sides, 121 minus 36 is just 85. And I already know that 85 is not a perfect square. So if I was to type in, my bad. Perfect, 85. So if I was to take the square root of 85, I would actually get a decimal in the end. I would not get a whole number. So here, this is just the square root of 85. Now, notice what the question is saying as well. Let me highlight it in yellow. Simplest radical form. That means we do need to reduce it using our factor, our prime factorization. Let me go back to my pen. So here, reducing the square root of 85, again, just pick 2 numbers that multiply to be 85. It ends in 5. That means we can divide it by 5. So 5 and 17 go into 85. Again, I just divided it by 5. I didn't know that off the top of my head. And then we keep going. So break up 5. Oh, wait. The only 2 numbers that go into 5 are just 1 and 5. Okay, so that means that's a prime number. Okay. 17. Oh, wait. The only 2 numbers that break up 17 are just 1 and 17. So we got another prime number. So in fact, the square root of 85 can only be broken up as 5 times 17, which is still, I mean, that's just the square root of 85. So actually, in this case, we have the simplest form already. But we still need to check because off the top of my head, I didn't know if it was or not. Okay? But in this case, our simplest form was already as that. Now I think we got 3 or 4 more here. We're going to find the third side in simplest radical form. Again, the same thing. In this case, though, I don't have a hypotenuse, so I need to find that. All right. So here, A, we'll just say it's 7. B, we'll say it's 6. And I'm trying to find C squared. Okay, so 7 squared is 49. 6 squared is 36. So 49 plus 36, actually, 49 plus 36 ends up becoming 85. Just like the last one. That was a coincidence. That was not on purpose. Um, but again, we need to get c by itself. So when I take the square root of both sides, wait, my bad. Let me go back to the pen. When I take the square root of both sides, we get that c equals the square root of 85. And normally, we would check if we can reduce this or if it's a perfect square, but we literally just did that. So that was an accident. Whoops. Did not mean for those numbers to be the same. Whoa, what is this? 15 on one side, the square root of 27 on the other. We're trying to find c. Okay, well, don't get freaked out. Let's just set it up as normal. So a squared plus b squared equals c squared. All right, so we're trying to find c. We don't have a hypotenuse, the side that's opposite the right angle. So that means 15 and square root of 27 are my a's and b's. And again, it doesn't really matter which one is which. So we'll just say 15 is a and the square root of 27 is b. Now here again, 15 squared is just 225. Square root of 27 squared. Now, you have a calculator, so feel free to use a calculator here. The square root of 27 squared is actually just 27. Again, this goes back to these exponent laws you should have learned in Algebra 1, because that can be written as the square root of 1/2, or as the power of 1/2. So when you add those two 1/2s together, you get 1. Students tend to remember it as like the square root and the square cancel out per se. But regardless, if I was just typing that in my calculator, you should still get 27. So if you're typing the way as it is, parentheses, square root of 27, parentheses, and square, you would get 27. So that's good news for us because I can just do 225 plus 27, and that'll be 252 equals c squared. Okay, and then from there, I'm like, okay, square root of 252, is that a nice whole number? It's not. That means we need to do some dividing here to break it up. So, well, first, let me get to that point. So when I did the square root of 252, it was a decimal. It was not a nice whole number. So let's break it up. I know that 4 and 63 goes into 252. If you didn't know that, you could just literally type in numbers into your calculator. Here, okay, 252 breaks up into 4 and 63. Okay, these are more doable. So for 4, we can say 2 and 2. 63, think about your multiples of 9. So 9 and 7. 2, we're done. 2 is done with. We're good there. 9, that can be broken up as 3 and 3. And then 7, we're done there as well. Okay, and again, what we're looking for here, so square root of 252, is we're looking for pairs. So once we get a pair, like we have a pair here and a pair here, and I'm going to again highlight this in a different color so you see where I'm bringing it. Every time I see a pair, I'm going to bring it, oh, my bad, to the outside. So again, this pair here, we'll do this green. So 3 would then go on the outside as well. And anything that's left over, I'll tend to box it up. And then that will go inside the square root. Oh, my bad, not 3, it'll be a 7. I tend to think of a corny phrase to help students. So the boxed up will go inside the box. Again, the box will go inside the box. So that's a 7, and that's a 7. But we can reduce that. We know that 2 times 3 is 6. If we don't know that, we have a calculator. So that says here 6 square root of 7 would be my value of C. Again, yes, the square root of 252 is correct, but the question says to reduce it to simplest radical form. Is that the last one? Yes, last one. Okay, cool. So third side again, it's the similar thing of like, whoa, one of the sides has a radical in there. That's kind of frightening. Don't be afraid. Plug in what you know. So that A is 12, that B is the square root of 20, and that C is what we're trying to find. So 12 squared we know is 144. Ooh, again, you can either use your calculator. Don't be afraid to use your calculator. Or if you saw from last time, whenever you square a square root, they quote unquote cancel out. So here, the square root of 20 squared is just 20. Now here, 144 plus 20 is just 164. And when I try to get C by itself, I would get that C equals the square root of 164. But unfortunately, the square root of 164 is not a nice whole number. I know it's tragic, but it is what it is. Now I'm testing because I'm thinking to do something in my head, and I'm pretty sure I'm correct, but I don't want to say it if I'm wrong. Perfect. So square root of 164, we need to write that in simplest radical form. If you're ever stuck on what to do, you can always divide numbers by 2. If it's even, divided by 2. In this case, I mean, it doesn't really matter. You can have 164 can be divided by 4 or 2. If it helps, I'll go ahead and say 2 and 82. 82 can be divided by 2 as well. We should get 2 and 41. And actually, 41 cannot be broken down anymore. But that's fine because we're looking for pairs. So a pair here we have is, we got that pair of 2 and box up everything remaining. Notice I didn't box up the 82 because I reduced the 82 as 2 times 41. So when I'm rewriting the square root of 164, I won't do the highlights this time. We take all of the pairs and place them on the outside, and anything boxed up, which is anything remaining, goes inside our square roots. So that says that 2 square root of 41 would be our final value for our hypotenuse. Now, there are different ways we will incorporate this, but we will need to know this for angle bisectors, and that's what we'll talk about in class on Thursday. Now, you should have covered this before in middle school, so this should be a refresher. If you're freaking out about this, please let me know. But if not, that should be it. It is perfect. Do you have any questions? Make sure to send me a Canvas message or an email. If not, I will see y'all in class on Thursday. I'll make sure Davey knows that we finished this video. Hopefully he's okay. I should probably check on him.